Kavita madam, please start.
A very wonderful morning to one and all. Today, on of applied scientists, Parul University, Asal Gupta, welcome you all to this today's scheduled webinar for the subject of mathematics, and the topic is. For this talk, we have with us a very renowned special personality, Dr. Bhadresh Dave sir. So it is my immense pleasure to introduce Dr. Dave sir as professor at Department of Mathematics, Faculty of Science in MSc. Experience as well worked out more than 40. Sir was awarded with his doctorate degree in the year 1995 for his remarkable research of the area of matrix series. Sir has presented more than 10 research at national as well as international conferences.
It's already 11:40. 11:40 थी.
In more than 10 times this topic. Of marriage, research related and works on history of academic. And what is the Association of School University seat. I invite Dr. Bhadresh Dave sir to begin you, sir. So you can begin your talk.
ये जो इनको कई भी मतलब आवाज ना जो कोई क्यों कई बार तरह कई लोग होते हैं नहीं हो गया व्हाट्सएप पे
મેં વિડીયો કર્યો પણ દેખાતો નથી વિડીયો. ये असेसमेंट से क्या आया तो ये क्या बता रहा है वन असाइन बोले तो
आपको एक बंडल असाइन किया ऐसे एक बंडल असाइन
वो तो हो गया तो
ये खाली असाइनमेंट की लिस्ट चाहिए सर पेंडिंग की लिस्ट नहीं है
हाँ,
तो हमें नहीं पता
can you hear to me? Hello, am I audible to you?
Yes, sir, you are completely audible.
Hello,
Please begin.
am I audible to you? Hello.
Yes, sir. Yes, sir.
कविता मैं बोल रहा हूँ सुनाई देता है? हाँ हाँ. Hello everybody, respected head of the department, the staff members, dear students, if
they are in the meeting. I just thought that topic I should select that must be slightly deviating from the usual study during our BSc, MSc study. And also at the same time, it should not be that much tedious or difficult. And also I took care that it has some utility, okay, in our familiar topics. So thinking these things, I chosen infinite product theory. I will be taking in brief the beginning. Actually, we are very much familiar with the infinite series theory. You see, when we think of the infinite geometric series, sigma x raised to n, 1 plus x square and so on. And we also know that this geometric series is convergent if absolute x is less than 1, okay? And the value to which it converges is 1 upon 1 minus x. So same way we came across the power series of sine function, which is series minus 1 raised to n, x raised to 2n plus 1 upon 2s plus factorial. Series converges to sine x for every real x. Similarly, series for cosine x, hyperbolic sine cosine functions, exponential function, logarithm function, etc. power series are known. Okay. These are infinite series, we know, and that's why we require to test the behavior. We say series converges if absolute x is less than 1, that is from the test of the infinite series for the convergence. Okay, we apply ratio test and we come to the conclusion that series converges if x between -1 and 1. Okay, so that's why sometimes we have the restriction on value of x for convergence. Sometimes there is no restriction on value of x in case of sine, cosine functions, exponential function like that. So in parallel to this theory, we have the infinite product, development of the infinite product, and why it was required to develop infinite product. Okay, that also we shall see, the utility. Okay, so we first consider the infinite product form A, that is a plus 0, a plus 1, a plus 2, a plus 3, and ending at a plus n minus 1. So we have total n factors considered in this product. N is any natural number, and a is complex in general, but such that none of these values is 0. Neither a is 0, a is -1, nor a is -2, nor a is -3, like that. So a is in fact complex number, but 0, -1, -2, all these values are excluded. Okay. This is symbolized as a sub n, spoken as a sub n. First factor is considered here, and total number of factors, that is written as the suffix place. So this is a sub n, and this is Poshamer symbol. This is called Poshamer symbol due to Poshamer. So we have the definition for n belongs to n. A sub n, if n belongs to n, a sub n is a plus 1, a plus 2, etc. But if n equal to 0, then definition a sub 0 is 1. So if there is no factor in the product, okay, then we know that identity element always there in the product. So definition of a sub 0 is 1. Okay. So now we consider the general form of the finite product. So instead of a plus 1, a plus 2, and so on, there is slight change made in the factors, and form is 1 plus A1, 1 plus A2, 1 plus A3 up to 1 plus AN. Symbol is product 1 plus AK, K from 1 to N. Okay. So we will be now dealing with this form of the product, 1 plus something. So A1, A2, A3, etc. are not equal to -1 to avoid the presence of zero factor. Here we have to take care of that thing. So AKs are not equals to -1 for all K 1, 2, 3 up to N. Okay. Now, likewise, in the theory of infinite series, there we have partial sum. Here also we have partial product. Okay. Notation is Pn. So this itself is partial product. Product K from 1 to N, 1 plus AK. This is partial product. And because there are N factors, it is denoted by P, capital P suffix N. So this is partial product. So if we take N tend to infinity, then we get infinite product, and this becomes its partial product. Okay. So that is what I have written, that the product 1 plus A1, 1 plus A2, and so on, that is product K equal to 1 to infinity 1 plus AK, has partial product given by K, product K from 1 to N 1 plus AK. Now, because there is infinite product, there is requirement to test the behavior, whether product has finite value or infinite value. In case of infinite value, we call it divergent, right? In case of finite value, we call it convergent. Convergent criteria is somehow differing from the convergence of theory of infinite series. And that's why this theory has the flavor. You see, if everything goes parallel, then theory will lose the interest. But here we have slight variation, slight change in the convergence criteria. Okay, so let us have first criteria of convergence. If the partial product Pn tends to non-zero finite number as n tends to infinity, then the infinite product will be convergent. Okay. And this non-zero finite value is the value of that infinite product. So advantage of first criteria is that it gives also the value of the product when it converges. Now see, note one thing here, non-zero. Zero is also finite value, but for convergence, this finite value as the result of limit must be non-zero. And why it is non-zero? Wait for some time, we come to the justification. We give the justification for this non-zero word, okay? You may have the natural question, so wait for that. We will be replying. So this is first criteria. Okay. Yes. So we consider the product n from 1 to infinity. We illustrate this first criteria here. So we consider product n from 1 to infinity 1 plus, now an are 1 upon n into n plus 2. These are an. Okay. So let us now have the consideration of partial product. We simplify that partial product expression. Then we take limit n tend to infinity and examine whether value is non-zero finite or zero or infinite. Okay, so let's do it. So we begin with the partial product Pn. Product K from 1 to n, 1 plus 1 upon K into K plus 2. And let us proceed for the simplification. So we simplify this expression. It is K square plus 2K plus 1. Right, giving us K plus 1 whole square, denominator as it is. So we now put the value of K, that is 1, 2, 3 up to n, and write the numerator and denominator numbers, 2 square, 3 square, etc. 1 into 3 into 2 into 4, then 3 into 5, n into n plus 2. Okay. All right. and then we group 2, 3, 4, n plus 1, again 2, 3, 4 up to n plus 1, and here 1, 2, 3 up to n, and 3, 4, 5 up to n plus 2. Okay. So in that case, simplification will be n plus 1 upon 1, okay, and here 2 upon n plus 2. So this is Pn now. And you know that limit is 2 upon 1, that is 2, as n tends to infinity. So Pn tends to 2 as n tends to infinity. 2 is non-zero finite number, right? So infinite product converges, and value of the product is 2. So this is additional information we are getting from the first criteria. Okay. Yes, this is what we have. So product is convergent. So this is illustration to first criteria. Okay. Thing is that it has the limitation. This criteria has the limitation. Having given any form of infinite product, it is not always possible to simplify Pn to a nice simplification form so that we can apply n tend to infinity and come to the particular number. It is not always possible. Okay. So there is requirement, okay, in lieu of this criteria 1, what other tools available so that one can test the behavior. For example, you see this product, n from 2 to infinity, 1 minus 1 upon n raised to p. P is any non-zero number. Now, because p is any non-zero number, we cannot simplify partial product. Okay, p is not fixed. That's why there is requirement to develop the other convergence tests. And this is the outcome of that. The product 1 plus an, n from 1 to infinity, assuming that there is no zero factor, okay, turns out to be absolutely convergent if and only if the series an is absolutely convergent. And here you see very interesting connection with infinite product and infinite series. Interesting in a sense that we are very much familiar with the series an and its testing. So by means of this, we can immediately come to the conclusion of the corresponding infinite product 1 plus an. Okay, so this is very, very useful theorem. And if we use this theorem here, above product 1 minus n 1 upon n raised to p, then an is minus 1 upon n raised to p, an. So sigma an is minus sigma 1 upon n raised to p. Okay. And we know that this is p series, if you recall, undergraduate infinite series course. The sigma 1 upon n raised to p is p series, converges if p strictly greater than 1, otherwise diverges. Okay. And therefore, this infinite product converges absolutely if p is strictly greater than 1. So we immediately come to the conclusion regarding the behavior of the series. Okay. All right. So this is what I said. Okay. This is what also I said, that partial product criteria 1 provides the value. Here we do not get the value. We just come to the conclusion about the behavior. And to get the value, one has to specialize value of p. Okay. Any value greater than 1. And then one has to apply the further criteria to get the value. For example, if p equals to 2, sigma 1 upon n square is known through the Fourier series, okay, which we are not covering due to time limitation. But you studied Fourier series, and 1 upon n square series n from 1 to infinity. So it is pi square by 6, its value, okay, through Fourier series. So there are many tools for particular value of p. Okay. We recall earlier I said that convergence of the product needs the non-zero finite value. Okay, so we now take up this. And a question again, I repeat, why non-zero value? So the following theorem that answers the question. Yes. See, there is another tool connecting to infinite product 1 plus an. We are on the way to answer that question, non-zero factor. So infinite product 1 plus an and series log 1 plus an, both together converge or both diverge. If one is convergent, other will be convergent. If one is divergent, the other will be divergent. Okay. So in this context, if you consider partial sum of this series, or let us consider partial product. Yes, I have considered partial product. So log Pn, it is when n equals to 1, it is log 1 plus a1 plus log 1 plus a2 plus log 1 plus a3. So, and we know that log a plus log b is log ab, right? So this is what I have written. So it is log 1 plus a1, 1 plus a2, 1 plus an. Now, if we make n tends to infinity, both sides, okay? Logarithm is continuous function for Pn to be positive. So limit of log is log of limit. So limit of log is log of limit. So here it is log Pn. Got it? This is Pn, partial product. So log Pn, so log of limit n tend to infinity Pn. Suppose Pn tends to 0. So this will be tend to log of 0. Log of 0 is known to be minus infinity, right? So series diverges. The one series diverges, that product diverges, right? Got the point? And therefore, for convergence of the infinite product, limit of partial product must not be 0. Okay, it is any finite value other than 0. So this is the theorem that helps to answer the question for non-zero finite value. Okay. Yeah, so this is what we had the discussion. So 0 value is not permitted. Okay. Yes, see, in this case, product is said to diverge to 0. This is not the terminology in infinite series theory. Please take note. So we have product either convergent or divergent, diverges to 0. Okay, and there is fourth criteria, converges to 0. Converges to 0 is that criteria in which 0 factor is involved. An infinite product with non-zero factors that converges to non-zero finite number. So 0 into non-zero finite number is 0. So product said to converge to 0. Okay. Here product said to diverge to 0. That's the thing. So this is how theory of infinite product differs from the theory of infinite series to some extent. In the behavior especially. Now, if Pn, limit Pn is infinity, then product is said to be divergent. Okay. All right. So this product is divergent because partial product PR is e raised to half, e raised to 1/3 up to e raised to 1 upon r. So e raised to sigma 1 upon n. And we know that series 1 upon n is divergent, harmonic series. So value is infinity, e raised to infinity is infinity. So limit PR is infinity. So product e raised to 1 upon n is divergent. Okay. See, seemingly n tends to infinity, 1 upon n tends to 0. and e raised to 0 tends to 1 is 1. But it is not the case. Okay, we have to critically analyze what is the actual expression of partial product, then to take limit, and then to come to the conclusion. Okay, so what is seemingly the value is not the case. Okay. Now we take the illustration of product diverges to 0. Take this one. Product e raised to minus 1 upon n. Okay. Partial product PR is e raised to minus sigma 1 upon n, e raised to minus infinity, value is 0. So product said to diverge to 0. Okay. Converge to 0. See, when n equal to 1, 1 minus 1 is 0. So 0 factor is there. So remove it and take n from 2 to infinity. Okay. So see, n equal to 1, 0 into this. These are the factors for n equal to 2, 3, 4, like that, for partial product. So it is 0 into this limit, 0 into finite value. Resultant is 0 because the presence of 0 factor. Otherwise, product converges, non-zero value. Okay. So 0 value because of the presence of 0 factor. So product is said to converge to 0. Okay. All right. Now we come to the use. I am slightly little bit quick to take care of your time. It is 12:07. Okay. Yeah. Now we see where it is occurring. Gamma function is largely affected because from the study of theory of improper integral, we know that integral 0 to infinity e raised to minus t, t raised to z minus 1 dt is improper integral of first kind because range of the integral is infinite. So it is improper integral of first kind. This is not a definite integral, right? And if real part of this variable z is positive, then theory of improper integral says that integral converges to function of z, and that function of z is denoted by gamma of z. We know this thing at our undergraduate study. Okay, we studied that. So this is improper integral of first kind, converges when real z positive, value to which converges is function of z called gamma z. Okay. Now, what is the validity region? Real z positive. If z is x plus iy, then we have complex z plane representing x-axis and y-axis. So x greater than 0 is the region of validity. I show to you. Where is the figure? Just wait. Oh, figure is not coming. No. But anyway, no, that is not the figure of that. It is green colored figure. Somehow it is not coming. But it is simple, okay? That x greater than 0, so first quadrant and fourth quadrant of the z plane. Region is easy to identify. First quadrant and fourth quadrant, excluding y-axis, automatically excluding origin also, right? So this is what the region of validity of gamma function. So it is evident that gamma function is not valid in second quadrant and third quadrant whole, including negative x-axis, right? So this is the limitation of region of validity of gamma function. One has to work only in first and third quadrant. One has to leave entire y-axis, right? So this is what. But because there is no other way out, one has to restrict work with the restricted region. Okay. This is what. Now, Weierstrass defined gamma function in entirely different manner. Weierstrass defined, this is Euler integral of gamma function, we know. Euler integral of gamma function. But Weierstrass took gamma function in entirely different way. He defined in this form. For n belongs to n, 1 upon gamma z, Weierstrass defined reciprocal gamma function. See, original definition reads this. 1 upon gamma z equals to z into e raised to gamma z, where this small gamma is Euler's constant. So e raised to gamma z, infinite product n equal to 1 to infinity, 1 plus z by n e raised to minus z by n. So this is definition of Weierstrass. An infinite product occurs here, okay? And naturally, we require to investigate the behavior, right? So considering partial product or considering the sigma, connecting this with sigma an. So 1 plus an is this. Our 1 plus an is this. So an is this minus 1. 1 plus z by n e raised to minus z by n minus 1. That will be an. So we now consider the sigma of this term. Test the convergence. Here tool used, I am not going into detail for the testing of convergence of that series, but tool use is limit comparison test. You know, but I just revise it. Limit comparison test says this. Given sigma an for testing the behavior, we consider sigma bn whose behavior is known, either convergent or divergent. Then we take limit n tends to infinity an upon bn. Now, if this limit is non-zero finite, then sigma bn converges, makes sigma an converges. Sigma bn divergent implies sigma an divergent. If limit an upon bn is 0, sigma bn is convergent, then sigma an is convergent. But no conclusion for limit 0 and sigma bn divergent, no conclusion. But if limit an upon bn is infinity, sigma bn is divergent, then sigma an is divergent. So this limit comparison test is used to test the behavior of series 1 plus z by n e raised to minus z by n minus 1. And value turns out to be non-zero finite, okay, resultant value. And therefore, infinite series converges absolutely. And therefore, this product converges absolutely. Okay, so this is the tool. This is the way to check the behavior of the product, infinite product. Okay, so let's proceed. Yes, now you see, let me just go back to that. Now you see, let us have the region of validity as compared to real Z positive. If we take the reciprocal of 1 upon gamma Z, then it is gamma Z. Z goes into denominator. And Z plus n upon n will be reverted. So it will be n upon Z plus n. So we have 1 upon Z. Then if n is 1, 1 upon n upon Z plus 1 upon Z plus 1, 2 upon Z plus 2, 3 upon Z plus 3, like that. Okay, there is no problem with these exponential functions, whether in denominator or numerator. But these matters when we take the reciprocal expression. So gamma Z is not defined for Z equal to 0, minus 1, minus 2, and so on. Because we have 1 upon Z, we have 1 upon Z plus n. So gamma z is not defined for z equal to 0 and each negative integer. Now this is complex valued function gamma z, right? So we say gamma z is not analytic at 0 and at each negative integer value. Elsewhere it is analytic. Okay. I assume that you know what is analyticity. Function, complex valued function is said to be analytic at a point z0. See, analyticity is related phenomenon. Analyticity at a point. Okay. So it is said to be analytic at z0 if that function is differentiable at every point of some neighborhood of z0. Okay. So this is what analyticity. And differentiability is function is differentiable at z0. Then we say that it is that is usual meaning. But analyticity refers to the neighborhood of a point, and at every point of that neighborhood, function turns out to be differentiable. Okay. For example, 1 upon z minus 1. So at 1, function is not defined. So in every neighborhood of point other than 1, function is differentiable. Okay, at 2, at 3, at 4, at I, 2i, 1 plus I. So function is 1 upon z minus 1 is analytic. Okay, so you know this thing. Okay, so here, so this is region of validity. Now you see. Except y-axis, except x equal to minus 1, x equal to minus 2 axis, x equals to minus 3 axis, except at these values 0, minus 1, minus 2, minus 3, everywhere gamma function is valid if it is defined in terms of Weierstrass infinite product form. So region is now enlarged. Okay. So here, then here, then here, then here, then every infinite strip on the left-hand side of y-axis. Okay, open infinite strip, of course. Now we have the extended region of gamma function. So people happy to work with the, but see, one has to then drop the integral form of Euler and accept the Weierstrass infinite product form. And for that, one has to be familiar with the convergence theory, fundamental theory, okay, convergence, etc. Then one is comfortable to work with the Weierstrass definition with this advantage. So Z can be taken to be minus half, minus 1/3, okay, minus 5/3. So this type of negative integer values or any point in third quadrant, fourth quadrant, okay, except these negative integral values. So gamma function is very well defined. Okay, so this is advantage. An infinite product involves here. That's the thing. Okay. This figure is not appear. That is for real Z positive. Somehow it could not appear. So this is what we just discussed. So these are singularities, right? Function is not defined, so singularities. This is what we discussed. Whole complex Z plane except for 0 and negative integer. Okay, now this definition is useful in deriving some other elementary properties of gamma function. Gamma 1 is 1. We frequently use this. So one can verify this property from infinite product. Infinite product helps us to evaluate the derivative of gamma z at z equal to 1. That is gamma dash z at z equal to 1 is minus Euler's constant. Actually, see, Euler's constant has approximate value 1.575, something like that. Okay. It is Euler's constant. This is another infinite product form of gamma function that is also obtainable from Weierstrass definition. Okay, we have limit expression for gamma z, n factorial n raised to z upon z, z plus 1, z plus 2 up to z plus n. And again, you see that z should not be 0, -1, -2, etc. Okay, in order that gamma z remains valid. And this is exponential function occurring in numerator n raised to z. Number raised to variable is exponential function, not only e raised to z. Okay, any number raised to z. Okay. Yes. Gamma 1 plus z is z gamma z, very useful property. And from this, if z is positive integer, we come to the expression that gamma n plus 1 is n factorial. So this is gamma n plus 1 is n factorial is from this particular property. Gamma 1 plus z is z gamma z. When z is positive integer, we have that n factorial expression. Okay, fine. Yes, property number 4, let me just show to you. It is in terms of limit. Very useful one, very useful property. You see, at beginning, we had the Pochamer symbol A sub n. It is A plus 1, A plus 2, like that. So this is Z, Z plus 1, Z plus 2, like that. Okay. So this is Z sub n. Z sub n. Now there is one identity connecting this Pochamer symbol and gamma function. Is that Z sub n, or let us take A sub n, is equal to gamma of A plus n upon gamma A. I repeat. Identity connecting Pochamer symbol with gamma function is that A sub n equal to gamma A plus n upon gamma A. So this denominator factors will be gamma z plus n upon gamma z. Now denominator of denominator will be numerator. So we have n factorial, n raised to z, gamma z upon gamma z plus n. Now both sides gamma z occurs and gamma z is independent of n. So we can remove it. So we have here 1 is the value of limit n factorial n raised to z upon gamma z plus n. That is what is the expression in remark, this one. This is useful. We see in what way it is useful. Okay, so we have Weierstrass definition. Then we come to property number 4. Then we use the relation between gamma function and Pochamer symbol and come to this particular limit. Okay. See the sequence. In what way it is useful? We take one illustration. This infinite series, n from 0 to infinity, gamma A plus n into gamma B plus n upon gamma C plus n, n factorial z raised to n. When it is tested for convergence using ratio test, outcome is that series is absolutely convergent for absolute z less than 1. Open disk in complex plane, centered at origin, radius 1. That is the region of convergence of this series. But then there is a question, what happens when absolute z is equal to 1? That is, z is either plus 1 or minus 1 on x-axis. Okay, even on y-axis, absolute I is 1, right? So either points on y-axis or points on x-axis, what is the behavior of the series? So to investigate behavior at absolute z equal to 1, that is on the every point of the unit circle, okay, boundary of the disk, this particular limit is used. taking Z equal to A, Z equal to B, Z equal to C. These are put, factors are adjusted, okay, and then the test is applied, okay, limit comparison test is applied. So that comes to the conclusion that the series on the circle absolute Z equal to 1 in complex Z plane converges subject to the condition real part of C minus A minus B is greater than 0. So this product helps to investigate the behavior of this type of infinite series on the boundary of the circle, boundary of the region, absolute Z less than 1. So boundary is absolute Z equal to 1 and series converges, okay, if real part of this is positive. There is someone, yes. After finishing talk, please switch on speaker so that you can listen to me. Lecture must. Okay. Oh, yes. Plus you also, if I forget, you just call me up. Okay, phone is here. I may forget. And the value to which the series converges is this. See, on the boundary of the region, the series converges to precisely this value, gamma function. Okay, value is in again terms of gamma function. And this takes care of the validity, okay, of gamma C minus A minus B. That takes the care. Denominator gamma functions are not to be taken care of. Why? If gamma C minus A is not defined, then it is infinity, 1 upon infinity is 0. Same thing with gamma C minus B. So we don't bother for denominator gamma function. Please take care. Okay. Numerator gamma functions are very much to be taken care of. Okay. Let's proceed. I think your time is going. Oh. I am strictly warned, okay, that I cannot proceed after 12:30. Kavita, is it? Kavita is very tough to me. Okay. Where the other occurrence of the infinite product? We summarize. See here. This is this theorem. It is in complex analysis. Very typical theorem. If Fz is expressible in terms of this infinite product, F is entire function, everywhere analytic. So entire function, En is sequence of non-zero values of F. I just, it is repeated. Multiplicity included, and Fs 0, a Z equal to 0 of order M. Then there is entire function G and sequence Pn of this type. But my point is infinite product occurs in complex analysis where function E is this one. E0Z is 1 minus Z and EPZ is this. Okay. So this is one occurrence. Another occurrence here. Complex valued function sin pi Z upon pi Z is expressed as infinite product this. Cos pi Z expressed as infinite product this. Okay. We have pi by 2 also expressible as infinite product this. Okay. See this interesting outcome where the infinite product is occurring. Okay. Last formula is known since 16th century. Professor Wallis in Oxford, he presented that pi by 2 is expressed. So infinite product is known. Okay, see 1616 is period 1616 to 1703. Professor Wallis. So known for quite a long time. Okay. In number theory also there is infinite product occurrence. Okay. We know what is prime number. It is number greater than 1, no divisor except 1 and the number itself. Okay. So these are prime numbers beginning with 2. We know it. So infinite product is where P runs over the prime numbers 2, 3, 5, 7. So product runs over these values only. So this product states that there are infinitely many prime numbers. Okay, that is what the occurrence. Riemann zeta function is this, and relation with infinite product is this. Riemann zeta function again expressible in infinite product. P again runs on the prime numbers. Please take care. Yes, P runs over all primes. If S equal to 1, this is divergent. See, this is divergent, so value is infinity. So therefore, we have the number of primes infinite. Okay, that's the thing. Yes, here it is. So product diverges, so number of primes is infinite. So that is from the infinite product convergence divergence theory. Okay. Yes, complex valued sequence Fn is multiplicative if F1 is 1, Fmn is Fn, Fm, where Mn and are relatively prime. Okay. Completely multiplicative for all Mn, this representation holds. And in terms of these functions, we have sigma Fn again expressible in infinite product. These are pk's are all primes, kth prime. P1 is first prime, P2 is second prime, okay, 2, 3 like that. Okay, so a product is absolutely convergent. And for completely multiplicative function, again, this is the representation of infinite product. So these are the occurrence in number theory, okay? And these are very simple exercises, very, very simple, very, very simple, very, very simple, very, very simple, okay? You are all teachers. To students, this is exercise. Just take the help of sigma this, sigma this, sigma this, sigma this, sigma this, sigma this. Here it is written. Okay. This is written to come to the value of the product or just investigate the behavior. Yeah. And what I used, Tom Apostle's book, Conway's book, Renville's book, then Slater's book, and Talon's book for number theory. So these are my references. So I could finish taking 3 extra minutes. Sorry to take your extra time. Okay. Yes, now I am mute.
Yes, thank you so much, sir. I deem it a great honor and privilege to propose vote of thanks at this moment. We are really thankful to sir for exchanging his expertise in area of various kinds of series. Thank you for introducing new symbols, theorems about convergence criteria of infinite products, connecting infinite series and infinite products, and make us revise the concepts of complex analysis, analyticity, etc., and making us aware of the applications of infinite product in the area of special functions, especially gamma function. Thank you for accepting our invitation and devoting your valuable time of yours for imparting knowledge to us. Finally, on behalf of whole Department of Applied Science and Humanities of Parul University, I extend my sincere gratitude to you, sir. Once again, thank you all for your attention and have a nice day. Thank you.
Thank you for your nice words. Okay.
Thank you, sir. You're most welcome. So here we have to end up this meeting. Thank you, sir.
Okay.
Bye, sir. Have a nice day, sir.
Bye.